Hey everyone, and welcome. We've all seen them, right? Those absolutely jaw-dropping photos from the James Webb Space Telescope. They're giving us the oldest look at our universe we've ever had, and they're even helping us find water on alien worlds. So today we're going to dive deep and figure out what these incredible discoveries really mean.
So here's the game plan. We'll start with what makes this telescope such a powerhouse. Then we'll get into its infrared superpower. After that, we're going to witness the birth and death of stars, look way back in time, and finally, this is the really cool part, we'll dig into the science of searching for life on other planets, including one very promising candidate.
And this quote from NASA? It just nails it. The Webb telescope isn't just snapping pretty pictures. No, with every single image, it is fundamentally changing how we see the cosmos. Every shot is a new discovery.
Now, a mission this revolutionary, well, it doesn't come cheap. This telescope took 25 years of design and development to build, and it costs a mind-blowing $10 billion. So what exactly did we get for all that time and money? What makes this the most powerful observatory ever built? Let's find out.
So what is the secret sauce here? What makes this observatory so special? Well, it's not just about its size. It's about the technology and its very unique parking spot out in space.
To really get what makes Webb so different, it helps to compare it to its famous older sibling, Hubble. Hubble, as you probably know, orbits the Earth, but Webb, it actually orbits the Sun. And here's the critical part. While Hubble mostly sees invisible light, the same light our eyes see, Webb is designed to see the universe in infrared. And that, as we're about to see, is its secret weapon.
To use that secret weapon, Webb has to be incredibly, unbelievably cold. We're talking minus 266.75 degrees Celsius. That's just a few degrees above absolute zero. To get that cold, it orbits 1 million miles from Earth at a special place called the L2 point, where it's always in Earth's shadow. And to top it all off, it's protected by a sun shield the size of a tennis court.
Okay, so let's talk more about that secret weapon, infrared light. This is the key. This is what lets Webb see things no other telescope has ever laid eyes on before.
So what is it? Well, infrared light has a longer wavelength than the visible light we can see. You know how radio waves can pass right through walls? It's kind of like that. Infrared's longer wavelength lets it slice right through these massive, dense clouds of cosmic dust and gas that would normally block our view, letting us see the secrets hidden deep inside. And Webb is actually packing two different types of infrared cameras. There's NICAM, which captures shorter, near-infrared light, and that gives us these breathtaking, wide-angle views. But then there's MIRI, the mid-infrared instrument. It sees even longer wavelengths, which lets it pierce through even thicker dust to see what's happening right at the heart of a nebula or a galaxy.
And with this incredible new vision, we can watch the entire cosmic life cycle unfold in stunning clarity, from the birth of brand new stars to the dramatic deaths of old ones.
Just look at this. This absolutely stunning image shows what scientists nicknamed the Cosmic Cliffs inside the Carina Nebula. This place, it's a stellar nursery. And all those tiny little red dots you see scattered around, those aren't distant galaxies. Nope. Each one is an infant star, just starting its life.
And just as we can see birth, now we can see death. This is the Southern Ring Nebula. Right in the middle, there are two stars. The dimmer one is dying, and it's shedding its outer layers into these huge clouds of gas and dust. This is what the end of a star's life actually looks like.
And the key thing to realize here is that stars have a life cycle, just like we do. And our own sun, it's on a very similar path. In about 5 billion years, it's going to swell up into a red giant, then shed its layers to create a planetary nebula, just like the one we just saw, before it finally ends its life as a tiny white dwarf.
Okay, so beyond seeing the life of stars, Webb is also a time machine. And I mean that literally, because light takes time to travel across the universe. When we look at really distant objects, we are actually looking into the past. This was Webb's very first deep field image, and it shows a galaxy cluster called SMA CS0723. But the real magic here is a phenomenon called gravitational lensing. The massive gravity of the galaxies in the foreground actually acts like a giant cosmic magnifying glass. It literally bends and boosts the light from even more distant galaxies hiding behind them, some as they were more than 13 billion years ago. And check this out, this is galactic interaction on a truly grand scale. This is Stephan's quintet.
Now, the galaxy on the left is actually way closer to us, but the other four, they are locked in this incredible cosmic dance, their gravity pulling and stretching and distorting each other. For scientists, this is the perfect laboratory to understand how galaxies merge and evolve over time.
As amazing as all of that is, maybe the most profound part of Webb's entire mission is the search for life beyond Earth. And to do that, it uses this absolutely remarkable technique.
That technique is called spectrography. And put simply, it's the science of analyzing light by breaking it down into its different component colors, or wavelengths. It's like a cosmic fingerprint. By seeing which colors are missing, we can figure out what something is made of.
So here's how it works. Imagine you shine a flashlight through a green leaf. The stuff in the leaf, the chlorophyll, it absorbs red and blue light, right? So only the green light gets through to your eye. It's the exact same idea with planets. When light from a star passes through an exoplanet's atmosphere, molecules in that atmosphere block certain specific wavelengths. Webb can measure which ones get blocked, and that tells us what molecules are there.
And using this technique led to a landmark discovery. Webb analyzed the light from an exoplanet called WASP 96b, and it found the unmistakable crystal-clear chemical signature of water, H2O. Now let's be clear, this planet is a scorching hot gas giant way over 500 degrees Celsius, so it's definitely not habitable. But this was a massive proof of concept. Webb can detect water in the atmosphere of a world over 1,000 light-years away.
So if WASP 96b isn't the one, then where should we be looking? Well, scientists have a prime candidate that Webb is going to be studying very, very closely.
I want you to meet TRAPPIST-1e. First off, it's pretty close by, cosmically speaking, only 40 light-years away. And it orbits its star right in the sweet spot, the so-called habitable zone. That's the perfect distance where temperatures could be just right for liquid water to exist on its surface. And this is where it gets really exciting. Look at how Earth-like this planet seems to be. Its radius, its mass, its density, its surface gravity, all of them are remarkably similar to our own homeworld. It's confirmed to be a solid rocky planet, which makes it, right now, the most worthy candidate we have for follow-up study in our search for life. So the James Webb Telescope is going to be analyzing this world in incredible detail, looking for water vapor, carbon dioxide, methane, the whole shebang. Finding the right mix of those gases could be a huge indicator of biological activity. And that leaves us with the ultimate question, doesn't it? If we do find the building blocks of life there, what happens next?